In this video, we'll look at a different method for finding the pinch point and the minimum utility requirements for a heat integration problem. Here we have two hot streams and two cold streams. The temperature interval method once again helps us find the location of your minimum approach temperature, aka the pinch point. And it helps you calculate the minimum utility requirements, both hot and cold utility requirements. So the first step in a temperature interval method for pinch analysis is selecting your minimum approach temperature. Once you have selected the minimum approach temperature, you have to adjust your stream temperatures. After you've adjusted the stream temperatures, you have to set up your temperature intervals. Then, in each temperature interval, you'll find the total energy gained by the cold stream plus the total energy lost by the hot stream for each interval. Then you'll find the residual heat once you have the total enthalpy change, total heat change in each interval. Residual heat for the network. Once you perform step 5, you will get the location of your pinch point and your required minimum heating utility and minimum cooling utility. In this video, we'll just do the first 3 steps and we'll look at the last 2 steps in a separate video. For this problem, let me select a minimum approach temperature of 10 degrees Celsius. Okay, now once again, the minimum approach temperature can be anywhere between 5 and 25 degrees Celsius. 10 is usually a good initial guess. Now our next step is adjusting stream temperatures. So let me go over what we mean by that. Now there are 2 ways you can adjust the stream temperatures. Your first option is to decrease the inlet and outlet temperature for your hot streams by a value equal to the minimum approach temperature. Or you can increase the inlet and outlet temperature for the cold streams by the same amount. Now, what both of these, by either decreasing the temperature of the hot streams or increasing the temperature of the cold streams, what you're doing in both scenarios is your pinch point, once you perform this adjustment, your pinch point is going to have a temperature difference of 0. And if you have a delta T of 0, that means your heat transfer, or let me say Q, is going to be equal to 0. So this is going to be important, like once we have our temperature intervals and we find the enthalpy changes in each interval. So this is the idea behind the whole the reason why we want to adjust the temperatures. There might even you might even see in some textbooks or some videos where you decrease by delta T min over 2 for hot streams and increase the temperature of the cold streams by delta T minimum over 2. And once again, this is following the same principle where the pinch point must have a temperature difference of 0, which consequently leads to the fact that the heat transfer across the pinch is going to be 0. And since all these three methods are equivalent, this should give the same final answer. So for the sake of this problem, we're going to go with the first option. We're going to be decreasing the inlet and outlet temperature of our hot and cold stream. So let me just copy these temperatures for our problem statement. Okay, so those are our actual temperatures. Now we're going to make a separate table for the adjusted temperatures. You have your source temperature and your target temperature. So the first two hot streams, we're going to decrease hot stream temperature by 10 degrees Celsius. So our 300 becomes 290, 150 becomes 140, 200 becomes 190, 50 becomes 40. So keep in mind you have to adjust both the inlet and outlet, both the source and target temperature. Now for the cold stream, we're gonna leave them as it is. Okay, so we have we've knocked out step 1 and step 2. So now we're gonna set up our temperature intervals. So basically you wanna all the temperatures that you find in your the values of temperatures that you find in the adjusted columns. We're starting off at the highest temperature that we have here is 300 degrees Celsius. The second highest is 290 degrees Celsius, followed by 190 degrees Celsius. And then we have, let's see, 140, 100, I think I missed 150, 150, 140, 100 degrees Celsius, 50, and 40. And notice that the width of each interval does not have to be so the width of the first interval is 300, 290. The width of the second interval is 290 to 190. So that's a difference of 100, but it's not drawn to scale here, and it doesn't really matter if it's drawn to scale or not. Okay, is that every temperature? Yeah, 40, 50, 100. Okay, that's all of our temperatures. So now let's start putting our streams here. Our hot stream H1 goes from 290 to 140. So that's going to go from 290, starts at 290, finishes at 140. So that's our H1 stream. Our H2 stream goes from 190 to 40. Starts at 190, goes to 140. Goes to 40, sorry. There we go. And we're left with both of our cold streams. Our first cold stream goes from 100 to 300. There we go. So that's C1. And C2 goes from 50 to 150. 50 all the way to 150. All right, so that knocks out our third step. Now in the next video, we're gonna find the what we're gonna do is for each interval. In this case, we have 1, 2, 3, 4, 5, 6, and 7. We have 7 intervals, and for each interval, we want to find the summation of energy lost by the hot stream and energy gained by the cold streams. So just to give you an example, for this first interval, it's just going to be the CP of cold stream, which is going to be, which is, if I, for our case, was 0.75. 0.75 times the temperature, the difference in the temperature interval, which goes from 290 to 300. So this is energy gained by the cold stream, so this is going to be positive. And as you'll see, in intervals where you have where you encounter multiple streams, we're gonna add and subtract the heat capacities depending on whether the stream is gaining energy or losing energy. So we'll cover the rest of this problem in the next video.